All right, guys. Hello. I haven't seen you, I think, 1 week again. I hope you had a good, restful vacation. And we continue with a review of calculus, and hopefully today we will have a very interesting lecture. I'm a bit down under the weather today, but hopefully the lecture is so interesting that you will not notice. So we did talk about limits of exponential functions, like limit of this sort. If I have 1 plus h to the power of 1 over h, that will give me e to the x. So this limit is e to the power of 1. Yes. And this limit is right away e to the power of -2. And this limit in f here is e to the power of x. I hope you understand several ways of how to attain it. It will become very important as we go on in this topic. And today we talk first about infinite series, just to remind us what those things are and how we understand them from calculus. So an infinite series is going to be a string of numbers that we add up, and the string of numbers appears not to have an end. And we write it using the sigma notation. From the first term added a1 to a2 to onwards, it's written as k starts from 1 to infinity ak. And in calculus, we understand this to mean the limit of partial sum. So this refers to the limit of a certain sequence, and that sequence is built up by summing up terms of another sequence. Yes, guys? So, for instance, the first term of the sequence is a1. Second term of the sequence is a1 plus a2. So you see it's a partial sum. So we are seeing it like this. First term, first plus second plus third, and so forth. So the nth partial sum is the sum of the first n terms, from first to the nth term. And the first theorem that we would like to say is what kind of summons must we have for the series to converge? So the first theorem is called the divergence theorem, and the divergence theorem tells us the following. The series does not have a chance to converge unless the sequence that we add up to, that we use to add up, is not converging to 0. Do you see why that should be the case? Let's see why that's the case, guys. So an, if s sub n is the nth partial sum, then a sub n is the difference between the nth and the n minus 1th partial sum. Yes, do you see that? In other words, to get to the point an, I can add up all the way to an and subtract everything added up to a sub n minus 1. And this is what we have here. Now look at this limit. This limit, if it exists, it is the limit of this minus that sequence. Now, Sn, by hypothesis, is going to converge to some number s. Sn minus 1 will have to converge to the very same number. Do you see that, guys? So how do I picture a sequence? I hope you picture a sequence in a similar way. So I imagine a column, and in the column, I imagine S1, S2, S3, S4, and onwards. You can imagine that? S1 is the first partial sum, S2 is the next, and onwards. And as I descend down the rows of that column, I should begin to see the same number. Do you agree? If the limit converges, then as I look down the column, I start seeing essentially the same number again and again. So if the infinite series converges to 1, then S1, S2, S3, S4, S5, finally, many of them might be very different from 1. But starting, let's say, from S100, S101, S102, all of them should appear to me as 1. And somebody with a sharper vision might begin to lose the distinction between 1 and the series once it gets to the 1000th count, right? Once it gets to the 1000th. But regardless, anyone looking down the column eventually starts seeing the same number, the convergent number. Do you agree? So what is Sn? S1, S2, S3, S4. Sn just represents a particular row that we are looking at in the column. So S100 represents the 100th column. Sorry, the 100th row within that one column, yes? And n-1 then represents the previous column. Do you agree that Sn-1 is just lagging behind? So it's just like looking at this row and looking at the one right above it. And if whenever I start looking down, I see the same number, then of course the one on top will look the same. So I hope it's intuitive to you why Sn-1 also converges to S, if of course the series converges. And that tells us that the sequence AN has to converge to 0. If we have convergence, the sequence AN has to converge to 0, which is of course intuitive, right? Because the difference between this row and that row is AN, right? And if AN is big enough, let's say if it's a number bigger than 1/2, then somebody who is able to detect a difference of 1/2, a detector that's capable of, that's fine enough to detect the difference of 1/2, will always notice the difference. And if the difference is 1/1,000,000, there might be a detector sensitive enough to still tell the difference apart. So that means that this difference has to melt to 0. Correct? So that's the divergence theorem. That's how we understood it in calculus. That's why if you know calculus very well, you might have said that what I mentioned, you owing me, which by the way, I still am waiting for my checks, that you owe me $128, you can object that in calculus you were told otherwise. Yes? But of course, guys, calculus is calculus. You should know that calculus means just this, means that you are expanding the sequence, right? That is what you think of calculus. And what I suggested is that I'm not going to wait to expand that sequence. I want it right away. If that makes sense, then perhaps you owe me $128. Good. So then how should we understand some specific series? We will need to know how to sum geometric series. They are very, very common. And you use geometric series when you use decimal expansion. So for example, guys, what is 0.333333333 and onwards? What's that equal to?
1/3.
1/3, thank you. Now, what is it equal to 1/3, guys? That's just a very common sum that you're very familiar with. So if I open that board, for instance, 0.333 onwards, right? It's what? It's 3/10 plus 3/10 squared plus 3/10 cubed and onwards. So as you can see, this is an example of a geometric series. It's an example of something like, in this case, 3. You can write it as 3 times 1/10 plus 3 times 1/10 squared plus 3 times 1/10 cubed and onwards. That's a geometric series. It's of the form a r to the m plus a r to the m plus 1 plus a r to the m plus 2. So you see, you have this term that you're multiplying by itself to a higher power. You're raising it to a higher power all the time, the r term, and you have the constant term. So that's a geometric series. How do we sum such geometric series? Well, that method with which we found out how much money you owe me is very useful here. So you can say, suppose that you're going to get something. So that something is right. Now, what's an easy trick that you can use here? You can see that if I put parentheses in here, what's in the red parentheses is essentially the same as the initial sum. What I must do to make it the initial sum, everyone at once, I must do what? You see, just if I expand it here, maybe I should write a few more terms. This is and onwards, n plus 2. So you understand it's going on forever. What would you do to the red parentheses to recognize that what's in the red parentheses is essentially the same as the original sum? What do I do?
factor something out.
Very good. And what? Factor R. Thank you, Nicholas. You just factor out R. Do you see why, guys? Just if I may, I will just factor out the R. Here is that R factored out. And then this is AR to the M plus AR to the M plus 1 and onwards. So that makes this expression equal to S. And I have that S equals to ARM plus RS. You agree? And that is very quick solution now. Now I know that S, just a very basic algebra, S is equal to AR to the M. I just move the S's across. It's divided by 1 minus R. And that's the geometric series solution, which you can, if you're worried that the summation is carried out to infinity, we can reduce the summation first to a partial sum, do this similar operation, and for a partial sum, I can show you what to do if you're interested, and you will obtain the same answer. Yes. So for our class, I hope you remember calculus well, guys. But I mean, this procedure is much quicker, and you could have come up with such procedure on your own. That's why geometric series are so easy to sum. And here I explain it again in case you missed it. Now, I would like to talk about Taylor series. We can use them here and there. So the simplest operations in mathematics, you learn them in the first or second grade. I'm not sure how it's in the United States. So those operations are multiplication and addition. You can think of subtraction as adding a negative number, right? And multiplication, just you understand what multiplication is. Essentially, it's integer multiplication. You can just afterwards generalize to rational numbers, how to multiply one rational number times another. So those are the simplest operations, and we would like, whenever possible, to represent any other operation in terms of them. Okay, so from that point of view, guys, polynomials are very, very important functions, because think about what is a polynomial, guys. What determines, so somebody in school might have defined a polynomial this way. A polynomial Px is equal to a0 plus a1x plus a2x squared, and until I get to some anx to the power of n. Yes, that's a definition of a polynomial that somebody might give you in the textbook, but what is a polynomial? Why would anybody care about this definition? What is it trying to capture? Now, if you look at this function carefully, you notice that it uses only multiplication and addition. Do you agree? And then the reason the polynomial is written in this way is that I group by how many times I multiply by the input, right? So a0 means I haven't utilized the input. Where I see x to the power of 1, it means I multiplied by the input once. X squared, I multiplied by the input twice. And you can think about it. Every operation that only uses addition and multiplication can be reduced to this form. You agree? If you take an input and all you do is add and multiply using that input by a fixed number, by a fixed collection of numbers, then you get this representation. Good? So that's what is a polynomial. And unfortunately, I think when you take calculus, you talk about things like infinite series or power series or Taylor series. And this name might prevent you from seeing what this thing really is. And from our point of view, it is an attempt to reduce things that don't look like a polynomial, things that are not right away utilizing addition and multiplication, to something where to simulate the same operation, but only using addition and multiplication. Clear? So for instance, if I ask you this question, is root of x a polynomial? Right? Let's just test if you understand. Right? So question, is root x a polynomial? First, could anybody tell me what am I asking? At this point, guys, you can also turn your camera so I can look at your faces. I'm starved of attention in society.
So you're basically asking if root x is of the form a sub 0 plus a1 x plus a2 x squared.
That's very good. And to make it just slightly simpler, you said it absolutely perfectly, but to make it slightly simpler, I'm asking, can you simulate taking roots? Because think about, guys, when you take root of 4, you are guessing that the number is 2, right? When I ask you what's root of 5, the reason you cannot right away tell me is because you do not have, perhaps in your mind, a procedure to carry this calculation right away, right? So what I'm asking, could there be a procedure that will simulate taking roots that only uses addition and multiplication?
Well, half to the power of 1/2 is the same as square root, but that may be different.
Yeah, but that's just a representation. When I write power 1/2, it's just a representation. The question is, do I actually use multiplication and addition when I do that? Right? In other words, can I actually make it like this, like what's written on the top, this form? Right? So because to say multiply a number by itself half the time, half the amount, it's not quite clear what it means. Why is it 1/2, right? If I say x squared, you're just saying take x and multiply it by itself. X cubed, it's x multiplied by itself 3 times. More or less, because we know how to carry multiplication, we can do it by hand, yes? You would know how to multiply 2 numbers by hand if you have to. So, any ideas? Is it a polynomial then? Well, we can think of it in terms of functions. Now, multiplication and addition work for all numbers, yes? But I cannot take roots of negative numbers, at least not in the real analysis sense. So that already tells you something is off. And if that's not a satisfactory explanation, you notice you remember derivatives are very nice for polynomials. You remember derivatives, yes, guys? Take the derivative of a polynomial that reduces the degree. Now, the derivative of a polynomial at 0 is defined, but the derivative of root of x at 0 is 1/2 root 0, which is undefined. So I can detect very quickly that there is a difference between root of x and a polynomial. Yes? Similar question. So the answer is, as I mentioned, is no, because p prime of 0 always defined. But derivative of the root is 1/2 root x, not defined at 0. Do you agree? So that's one easy way, very quick way that I can right away tell that root of x is not a polynomial. So what about e to the x? If let me call this function f of x, is it polynomial?
Yes. Wait.
I would say yes, only because I've seen the exponential function expressed as a polynomial, but I couldn't tell you what it is.
Well, perhaps you're right. And the question is, we see that the word polynomial right now is a sort of loaded term. The more precise question is it a polynomial that has a finite power, right? Because let's say a polynomial of degree 2 has power x squared as the biggest one, right? Polynomial of degree 3 has a power of x cubed as the biggest one, right? And onwards. So this gives you a quick way to deal with it. You see, so you know that if px is a polynomial, then the derivative of px, the degree of it, let me write it better. The degree of p prime of x is equal to, what's the degree of the derivative of a polynomial in terms of the polynomial?
-1.
Exactly, it's equal to degree minus 1. It's equal to the degree minus 1, yes? So if it's a finite polynomial, when I say polynomial here, I mean finite. It's a very crucial word. And so you see what happens on the other hand with f of x. If I take the derivative of f of x, I just get f of x. In Russian, we say like water from a goose's feather. In other words, it just doesn't stick. The derivative does not change the function and therefore would not change the degree. Do you see? So by this very simple act, I right away verified that e to the x cannot be a polynomial. Cannot be a finite polynomial. In other words, cannot be a polynomial that has the biggest degree. Good?
I have a quick question.
Yes, go ahead.
Yeah, in this equation, you're raising e to the x, but in the polynomial example you showed before, you were raising x to the n. So is that like a valid argument for why it's not a polynomial? Because
no, because first of all, if you think about it deeper, I mean, it's probability, so I am being slightly loose. In real analysis, I would be very thoroughly talking about it. E to the power of x, first of all, you ask yourself, does it even make sense? What is e to the power of x? What is that power idea, right? So a power idea does work for, let's say, e to the power of 3. It's multiplication. You agree? It's e times e times e. If, of course, I know what e is. I mean, the question is even what is e? I mean, I just gave you some limits, whatnot, but also very theoretical ideas, right? We haven't really explained what e is enough. But if I give you e to the power of 1/2, that means take the root of the number, right? And how do I do that, right? So, so the question is just, first of all, what is e to the x? And e to the x from a function theoretical point of view is a function, just a function whose derivative is equal to itself. That's what it is. And with the extra condition that at 0, it's equal to 1. So if I had to define abstractly what is e to the x, I would say, give me a function such that the derivative is the function itself. And at 0, the value is 1. Yes? So the derivative is itself and at 0 is 1. So e to the x, or basically what this thing is, it's a solution to this differential equation, if such a solution can exist. So it's very, very loosely defined here, right? Yes. So yes. So then what? And if you want a more thorough discussion, guys, of course, stay after class. I'm happy to tell you how I think of e to the x, what's the use of it, and anything like that, right? We can give some examples from physics that calculus students don't like. And, you know. So we answered a few of those questions, but then, guys, we noticed that the problem with e to the x when we said it's not a polynomial is that it was a finite polynomial. You understand? And the same problem we had when we took the derivative of root of x anywhere, right? You would see that if you allow for the idea of carrying addition and multiplication indefinitely, then you can capture the sense of many more functions than if you just have finite polynomials, okay? So Barry, when he mentioned that e to the x is a polynomial, he was right. But I would say add the word infinite polynomial. You understand? We have now this distinction. We have a polynomial that's finite. That's when you have the largest power, let's say power 5, 10, even a million, but there is a largest power. And we allow for an infinite polynomial where there is no largest power. And the technical term of it is power series. Okay, they call it power series, but you think infinite polynomial. That I think is simpler so that you connect the ideas, okay? So something that is not a finite polynomial may well be an infinite one. And that's a definition of an infinite polynomial, just all the same, except you're allowed to continue adding forever. Yes. And with this example, let's now try to think what happens if I suppose that e to the x is a polynomial. And again, guys, you can either imagine that you know that e to the x is some definite thing that you know how to differentiate and you saw graph of it or whatnot. If you think about it deeper, you would realize that you don't know what is e to the x at all and what it means to exponentiate. And there are many, many ways out of it. But one of them is to just try to solve the differential equation. In other words, from a function theoretic point of view, can you find a solution where the derivative of a function is equal to the function itself and the function at 0 is equal to 1? Okay, and see if you can find that solution. And that's what we're actually doing here. Okay, so suppose that we have a function. When you take its derivative, the derivative is unchanged, and we just suppose further that we can solve it by using infinite polynomials. You with me, guys? So just I do not know how to search for such function. I'm hoping I'll be lucky enough that it will be an infinite polynomial. You're with me? Wonderful. I hope I'm not confusing you too much, guys. You're with me, yes? So then let's look what happens. I take the derivative. First of all, I look at this infinite polynomial. All I know about this function is that at 0, it's equal to 1. Yes? And the derivative of the function is not changed. So I can use those things to figure out the coefficients of this polynomial. So for instance, if I plug 0 instead of the x, I kill or eliminate all the coefficients other than a0. And I see that f of 0 is equal to a0, from which it follows that a0 is equal to 1. Yes? Next, I will take the derivative of this function. I take the derivative of this function and plug in 0. If I take the derivative of this function, here it is. Do you see it, guys? I presume that I can take derivatives just like I did for a regular polynomial. Here is what I get. I now have a1 without an x. I plug in 0, everything is eliminated other than a1. So I see that f prime of 0, the derivative of this function, will have to be the coefficient a1. Yes? And if I carry this process onwards, just because of the power rule in derivatives, I will see that the kth term, if I take the k derivatives, I will have this expression. It will be k factorial times ak plus a bunch of other terms. I plug in 0, and I have that the kth derivative as 0. It's k factorial times a sub k. Are you with me, guys? You understand that the idea is this: you take this thing, and all you can do is plug in 0 and take derivatives, because those are the only operations that make sense to you for e to the x, let's say. You know the value of e to the 0, which is 1, right? And you know that the derivative is unchanged. And again, e to the x is completely non-existent at the moment. Nicholas, hopefully not confusing you there. I mean, we are solving the equation. Derivative of the function is equal to the function itself, and at 0, it's equal to 1. Yes, you can see for playing with exponential functions, or it appears that that's going to be the right limit for an exponential function. That's why we might have picked that guess. But if you're interested, guys, I can give you a more thorough description of it. So what you have is a sub k is this expression. A sub k, the coefficient, is the kth derivative at 0 divided by k factorial times x to the k. And here is your Taylor series formula. Okay. In other words, that any function that is expressible as an infinite polynomial, the coefficients of this function are going to be of this form. So the coefficient ak is the derivative of this function at 0 divided by k factorial. So this function is completely determined by what it does to 0. You understand? Now, how does it help us with e to the x? Well, we know that any derivative of e to the x is e to the x, and at 0, it's 1. So that tells us that this function e to the x is x to the power of k divided by k factorial, because it's always 1 divided by k factorial, because the function at 0 and its derivatives at 0 is always equal to 1. So it's 1 over k factorial is how we get here, right? And look at it. I can calculate with this function. I can carry out calculations. I can add the terms up to a finite number and get approximations to what I mean by it, right? So for example, I want to know what is e to the power of 1/2. I add a bunch of terms where I plug 1/2 instead of the x. Let's say add 10 terms or 100 terms. I can estimate how many terms I should add to get a very good approximation. That's what I will get. Okay. Now, in practice, you can show that a function, this infinite polynomial for all integers will satisfy exponential properties, and for all rational numbers will satisfy the exponential properties. In other words, this is what I mean. If I have a function defined like this, 1 plus x squared over 2 plus x cubed over 6 and onwards, right? Then you would find that f of x plus y is the same as f of x times f of y. So that's what if you remember, if you know, a to the power of x plus y is supposed to be ax, ay. Okay, so you will begin verifying that it has exponential properties. And for instance, you would find, because of that, you would find, let's say that f of n is equal to f of, it is equal to f of 1 to the power of n. So it has exponential properties. Okay. So you can play around with it, and you see that this infinite polynomial behaves like what you imagined an exponential function should do. And if you're interested, I can show you how it works, but of course later after class. And guys, of course, you should figure how to do the same thing. This is what I meant, Nicholas, again, right? This is a function theoretically what you begin with, the attempt to solve this differential equation, and you will see that the solution to the differential equation is unique. So there is only one thing that solves it. And then you can look at it and verify that it behaves like an exponential function. In fact, the first exponential function that perhaps you thoroughly understand. You should try this procedure, guys. You can try to see what the procedure to decompose sine x, cosine x, and other functions like that into Taylor series or into this infinite polynomials. Okay, just to see that you understood this process, but we especially need e to the power of x. Good. And now, are you ready for the interesting part of the lesson? I hope you are, because we're about to start talking about probability. Yeah, what is probability and what's its meaning and onwards.